And off we go. Okay, so this lecture and the other 4 that'll be in the coming weeks will be devoted to independence proofs. And of course, the forcing method of independence proofs. And so what is the problem, if you will? Well, this is the central question. Let us concentrate on the continuum hypothesis, but we will see that we can do many, many more things than that. But how to prove that you cannot prove something? And let's say in particular the continuum hypothesis. Any course in logic will tell you okay, what do we mean by cannot prove CH? From the axioms of ZFC, of course. Mathematical logic tells us that there is basically only one way to do this. It tells us that there is one way to do it, and Gödel's completeness theorem says it's basically the only way. Build a model of your theory in which the negation of CH holds. There are two things to Gödel's completeness theorem. One is what some people call the correctness theorem, that says if you have a proof from axioms of something, then that something will hold in every model of the theory. It says that if something can be proven, it is also a logical consequence, in the sense that all the models of the theory will have to satisfy that statement. And Gödel's completeness theorem goes the other way. It says that if you happen upon a statement that holds in all the models of your theory, then there must be a formal proof of that. And so if you want, it's an if and only if situation. You prove that you cannot prove it if and only if you construct a model in which the provable thing is not valid. Two difficulties here. The first difficulty is Gödel's incompleteness theorem. Well, the second, but let's say both together. Because the first is used in the proof of the second. How do we construct a model? Well, a model is a set where we assign to any predicate and any function letter in our language a subset of a power of the set, or a function from a power of the set to the set itself. These are the things that we assume you know from some course in logic that you have seen before. So building a model uses sets. And we're trying to build a model of set theory, and Gödel's incompleteness theorem says that's impossible. That's what Gödel's incompleteness theorem says for the theory ZFC. Well, that's sad. So that we can do two things now. We can give up and do something else for the coming 4 weeks, or we can try to get around Gödel's incompleteness theorem. And let's try to do the other thing, because mathematical logic tells us more, and in particular Gödel's completeness theorem, both sides of it, give us a little bit more, give us a little bit, shall we say, wriggle room to get around the fact that we cannot find models for the full ZFC. Because here is the thing: a proof of CH, if any, would use only finitely many axioms of the theory. We have, for ZFC, we have infinitely many axioms. We have a few that are single axioms, like extensionality, pairing, union, power set, choice, infinity. All are just one formula. And then we have two sequences of axioms for separation and for replacement, one for every formula in the theory, in the language of set theory. Some of those formulas are useless and we cannot do anything with them, but some of them, if chosen cleverly, help us along in a proof. But any proof is finitely long and uses only finitely many of those axioms. And even mathematical logic helps us here, because what I just mentioned about the logical consequence. So math logic says say phi 1 up to phi k. Let's call those axioms. I don't really care what they are. Math logic says if you want to defeat your proof, find an interpretation, and I'm very careful now, I don't say model, of what? Well, the language of set theory, and there's not much to interpret there, only the element of symbol, and if you want, the equality sign, in which phi 1 up to phi k are valid. Some people say true. Well, you can use other verbs that say the same thing, but CH not. And if you're looking in a structure, if a formula doesn't hold, then it's negation. CH is a closed formula, and if a closed formula does not hold, then its negation holds in the structure. So even that's all we need to do. We don't need, if we want to do that, we don't need to find a model for the whole theory. We can get by with models for finite sets of axioms, but then we do really need to take an arbitrary finite set of axioms and show how to do this, this miracle here. The rules of interpretations of formulas in languages, first order languages, tell us that this will defeat any problem. Because what does this do? It does not provide a proof in ZFC that CH is not provable, because we cannot quantify over sets of formulas. So it doesn't really say ZFC proves CH is not provable. What it does, it tells us outside the world of sets that there is no proof. That, well, let me be very careful here, that any proof of CH that we might find cannot be translated. So I'm writing this out in full because it's important that we get it straight into a formal proof. And by formal proof, I mean what you would have learned in a course of mathematical logic, a formal deduction according to the formal logical axioms, the formal inference rules. If you look at the book of Mendelssohn in chapter 2, that'll be modus ponens and the generalization rules and a few other things out there. There are also books that use what is called natural deduction, where you try to find a whole tree that will give you a proof of the of the statement, sorry, that you're looking for. But what we are going to do in the coming weeks will tell us is that there is not going to be a formal proof of CH into a formal proof. We have our first order theory ZFC. Did I say in? Well, maybe now let me leave it at that. It does tell us that we might decide that CH is true for some reason, but then that would need extra assumptions beyond ZFC. Right. And forcing is a method that lets us do this. It's a systematic way of doing this. It will let us, given a bunch of formulas, build a structure where those formulas are valid. And the one that we would like to prove unprovable is not. Okay, so that's the word that I was looking for, systematically. That's the first difficulty, well, let's say swept under the rug. We cheat a little bit. We simply say we cannot prove it from finitely many axioms. The advantage of this is that we can work back in ZFC again to construct those sets, as we will see today. And that brings us to the second difficulty. So the first difficulty was there's Gödel's incompleteness theorems. They seem to block the model building way. Well, we don't build models, we build structures, if you will. What's the second difficulty? Well, it is all quite technical. Unfortunately, there's no way around it. If you want to double is, that's a bit much. It is all quite technical. You need to know sets. Partial orders. We talked about partial orders a few weeks ago, but anyway, they are one of the main instruments in the forcing method. What else? Some derived notions, filters, then sets. They will all be defined later on, but I'm just, okay, I'm not trying to scare you, but I'm warning you that we'll be doing quite complicated technical stuff every now and then. And infinite combinatorics. That's one of the things that some people advertise forcing as a way of translating one combinatorial statement into another. And the other one gives you a result, a non-provability result. And the translation is straightforward. And so that means that you have to work to find that first combinatorial statement to prove it or discover it if it's not known yet. Those are the technical difficulties, and they will occupy us the last 4 weeks, I think. But we go today. I will try to tell you how this is going to happen. Let me make it red. And look closely. I don't have the CH in that bracket. I'm going to show you how to build a structure that satisfies any given finite number of axioms of ZFC. Next week, we will start discovering how to modify that construction so that you can build in other stuff that you don't want to be valid there, for example. Or you do want it, well, you don't want CH valid, but you want not CH valid or something like that. So how can we construct those sets M? And to create some confusion, but it shouldn't. And in the group interaction, there is at least one problem where you are asked to reflect on this. Believe it or not, but the M will always be countable and transitive. That's a very useful thing to have, as you will see in the coming weeks, because it allows us to do to make extensions of such models, and that is what forcing then is going to be all about. What will our interpretation be? Our interpretation of we are not going to do any graph theory, what was it, directed graph type models of set theory, because any one of those can be translated in one with the real epsilon relation. Anyway, what we will do, we look at sets, column M for the moment, with just the real element relation as the interpretation of element of. And of course, equality will be just equality in that set. And what's the, how shall I say this? What is the thing that we're going to be doing? Some of this we did in the first few weeks. You may remember that V omega models finite set theory. And how did we see that? Well, we saw that by just interpreting the element of relation as the element of relation and checking that all the axioms of finite set theory were valid in that structure. And how did that go? Well, we simply, I think, what we did was restrict all the quantifiers to V omega. And said, well, if we want to prove that pairing holds in V omega, we take two elements of V omega and show that the pair also belongs to V omega. If we want to show that union holds, we take an element of V omega, take its union, and show that it belongs to V omega. That kind of thing is what that modeling was all about. And we will be doing roughly the same thing. So, but we need to get our notation straight in this case. So let M be a set. We convert every formula into its, and I think this word was not in the title of today's lecture, but it's should have been there. We're going to take a formula and convert it to M. What we're basically doing is, in terms of model theory, we're going to interpret the predicates. Well, the predicates are the element of and the equality relation. And we already, I already announced what its relativation, and how do we write the relativation? We simply hang an M on the whole formula. So how is that going to happen? Well, like I said, element of is just element of. Equality is just equality. And if you want to keep everything a little bit, like I say, syntactically correct, you add a few parentheses here and there. But we leave most of the parentheses out for readability. And you can do this for all the symbols, but you can also say, well, I know it for the negation, I know it for the conjunction, therefore I know it for all the logical symbols, because I can express these in terms of negation and conjunction. And of course, This is the important bit of the definition. How do we interpret an existential quantifier? We interpret it as there is an X in M. And the short version of this is this. So we abbreviate the there is an X in M and phi as there is an X in M such that phi. For all X phi M, if we want to translate a universal quantifier, we first write it in terms of the existential quantifier, and then we translate that. But we will simply write what we get is logically equivalent to this. So we don't really bother. We take the translation of the universal quantifier as given by this short form here. Now, the reason why, again, the reason why I was so frugal in putting M's above formulas, I only do it for the element of, the equality, the negation, the conjunction, and the existential quantifier. The reason is that later in the coming weeks, we will be doing induction on complexity of the formulas, or length of the formulas, if you will. And then it's nice to have as few cases as possible. So if we need to check something for all formulas, we only need to check it for element of, equal, negations, conjunctions, and existential quantifiers. And once we have done it for that, the rest, the other abbreviations will tell us it also works for the universal quantifier and whatnot. So this is to reduce the workload later on. Okay, and much like in mathematical logic, let's keep that black again. If we can prove the relativation of our formula, we can simply prove it, then we will say that phi is true in M, or M satisfies phi, or phi is valid in M. Those are all synonymous. Well, let's look at, during the group interaction, you'll be asked to look at a few formulas to see whether they are true or valid, true, satisfied by transitive sets, because we're going to be working with transitive sets almost exclusively. Look at extensionality. That's one of the easiest formulas to write down. If we translate it into, if we put the M on top of it, we get this. Like so. For every X in M, for every Y in M, for every Z in M, Z is an element of X if and only if Z is an element of Y, implies X is equal to Y. we could abbreviate, or I don't know, write this slightly shorter as like so. For every z in M, z is a member of X if and only if z is a member of Y, means that the intersection of X and M and the intersection of Y and M are the same. Okay, and so here is our first result. If we have a transitive M, then M satisfies then M satisfies extensionality. I think we have seen this before, but since it's relatively short, I decided to use it as an example. And why is that? Well, because we can simply prove it in ZFC, the M version of extensionality, by noting that X is the same as the intersection of X and M by transitivity of M. And like I said, in the group interaction, you will be asked to look at a few results of this nature, where you check that things like pairing or union or whatever can be done. It's also a nice exercise to find models where things fail. You could try and build a tiny little M, which then of course is not transitive, in which the extensionality axiom fails. That's not too difficult, but we'll, like I said, it's a nice exercise. I make one assumption here. We are looking at finite sets of axioms of ZFC. And I mentioned already that there is a bunch of them that are basically just one sentence. And if we are talking about finite families of formulas, then there is no harm in adding those single sentences, because that only keeps the set of formulas finite. And it shows us that the real trouble is in the infinitely many separation and the infinitely many replacement instances. So we assume that extensionality, pairing, union, power set, why not? What else? Infinity, regularity, foundation, if they're not, we'll add them. And the point is that if we add them and we get an M that satisfies these, how many are there? 1, 2, 3, 4, 5, 6, 7. If we find a set that satisfies these axioms, then we can do a lot of set theory inside that transitive set already. And many things that we have proven to be equivalent, for example, rely on these finitely many axioms a lot. So if we know that they hold in our structure, then all their consequences hold in our structure as well. And that is really useful to have at times. And I will try to point out that this is useful where this is useful at times. Okay, so the ultimate goal now is so the ultimate goal will be and if we want to show that the continuum hypothesis cannot be proven, we're going to, the ultimate goal for the next few weeks, well, we'll do a few more things later, I hope, but one of our goals will be to find an M where our axioms hold and where the M version of not CH holds as well. But like I said, we're first going to look at this, and we'll worry about this later. The first part is, I'm going to say this relatively easy. It's not completely trivial, but it is quite straightforward because we assume, sorry. We assume that all the axioms hold in V, which is the union of the V alphas. And as a first step, the first step is going to be to find a V alpha such that the formulas phi1 up to phi k relativized to V alpha hold. Now, for the axioms, yes, I think, for the axioms, extensionality, pairing, union, power set, infinity, regularity, and choice, if we assume they hold in V, then they hold in V alpha for many limit ordinals V alpha. Because extensionality, we already saw that it holds in a transitive set. Pairing, well, the rank of a pair is just one up from the rank of its constituents. The rank of the union is at most one up. The rank of the power set is one up. Infinity has rank omega, so if we take a limit ordinal above omega, then we have omega in V alpha. Regularity is built in into V alpha. And choice, the same thing. If I have a family of sets, then any choice function of it, if I have a set that belongs to V alpha, then any choice function belongs to V alpha as well. If we relativize those to V alpha, then all we're saying is all the objects that we want already belong to the V alpha. Of course, that's nice to know. We could take omega plus omega already here. But what we want is the instances of replacement and separation. Okay, separation also holds in many V alphas. So the real trouble is going to be the replacement business. And how are we going to do that? Well, here comes the first tricky concept.
Okay, P, can I ask something?
Yes.
So I understand the first assumption that ZFC is consistent. It makes sense that we do it. But the second one, that the axioms hold in V.
Yeah.
Yeah, I don't really understand it because like V, we cannot create V in ZFC itself, right?
True, but
so it is like we are using a naive viewpoint or meta anyway, and from that point we can already sort of prove that the axioms hold.
In the naive way, V, yeah, we simply assume that V is so nice. Well, if we construct the union of the V alphas, then we actually proved that that union, that class, satisfies all the axioms, because extensionality is true by transitivity.
Mm-hmm.
Pairing is true because it's closed undertaking the pairs. Union is true because it's, and so all those, and again, the replacement axiom, since we're taking the whole class, if I have a functional thing and I have a set in its domain, I take the supremum of the ranks of all the images plus one, and then the range is a member of that certain.
Yeah, exactly. So I understand, but so in what way is it then an additional assumption?
Well, we assume that it is consistent, and that okay, we assume that all the axioms hold in V alpha in V, and for us that implies that V is a model, and so implicitly, you can say implicitly we assume that it is consistent.
That what is consistent?
Consistent means that you cannot derive 0 equals 1.
So that's ZFC is consistent.
Yeah.
Okay. Yeah, okay.
Because if ZFC is inconsistent, then we can prove CH
anyway.
Yeah,
of course, yeah.
And that wouldn't be very exciting.
Mm-hmm.
Okay.
All right, thank you.
Okay. Absoluteness, that is a notion that trips me up every now and then still. When I think something is absolute and it isn't. We'll try to, I will define this, and you really need to think about this a few times before you, I think before you really get it. But I put problems in the homework and in the group interaction to get used with this notion. Okay, so we have a formula. And we write this. We write it like so. To indicate that its free variables so some books are even worse, and they say, well, some of the x's may or may not be free, and so on. But what we want to do is we want to substitute elements of sets for those particular variables x1 up to xk, if possible. And you can only substitute for free variables. And so the variables in the formula phi that are free are among x1 up to xk. And we say among because every now and then we put a quantifier in front, and then one of the variables is no longer free, but we still want to keep that letter in the formula every now and then. It's nothing more than notation for now. M and N will be sets. They could be classes as well. And the only real class that we'll be talking about would be the class V itself. Otherwise, we'll be talking about sets mostly. Okay, if M is a subset of N, so absoluteness only works if one is a subset of the other. It's a little bit ugly, but absolute. It's not the vodka. Phi is absolute for M and N. Between M and N is something that I tend to say every now and then. Anyway, there is an interplay between M and N with regard to the function phi. Okay, I'll write down the definition. You can think about it. And in the second hour, then we'll have a break. And in the second hour, I'll talk about it a bit more. Because I want you to be able to stare at the definition for the next 15 minutes and absorb it. Phi is absolute between M and N, for M and N, for M, comma N. All those are synonymous if the following holds. Okay, this is ugly. For every k tuple of elements of n, now look very closely. What does this say? It says that if you have members of M and you want to check whether when you substitute those members of N, which are sets in themselves, you substitute them for the variables in phi, and then you, in the relativized version of phi, you substitute the members of M and you check whether you get a valid thing. You can also, because the M's are also members of N, you can take the relativized version to N and then substitute the M's on the free positions. What you want is that those two things, what you get, are equivalent. If one holds, then the other holds. If the other holds, then the one holds. This has got, what I'm going to write down has got nothing to do with set theory, but it is an instructive example. We have two fields, Q and R. I'm looking at algebra because this is the easiest example of non-absoluteness that I could think of. And phi x is this. What does it say? Well, x is a square. And so if I relativize this formula to the rationals, then when I stick in 2, which is a member of Q, I get something which is false. If I relativize to R and I stick in 2 on the position of X, then I get something that is true. So this formula is not absolute between Q and R. Like I said, it's got nothing to do with set theory, but it's one of the simplest formulas that I could find that is not absolute between two structures. And this is the kind of thing that you have to be looking at. You can, if you will, say that the m's form some kind of a solution to a set of equations, and the m's solve the set of equations if you use members of m as parameters, but they solve the same equation if you use the members of n as parameters. Anyway, look at this, stare at it for a while, compare it to the example of the, compare it to the field example, and we'll be using it a lot today, so I hope it will become clear. And we also will be looking at absoluteness between M, some set, and the whole universe. And if we are relativizing to the whole universe, we're not doing anything. So we don't really hang the V on the formula, because that's not necessary. Okay, this is the end of first hour. Like I said, stare at the formula for a while, and I'll pause the recording. Here we go. Okay, I want to make a few.
What are you doing?
Yep. I want to make a few comments here. There was a comment from Cheng Liao about, doesn't absoluteness mean elementarity? For those who know elementarity from model theory, elementarity means that all formulas are absolute between the two structures. So a smaller structure is an elementary substructure of a larger one if all formulas in the language are absolute between the two. So what we're talking about here is some sort of partial elementarity, if you will. We just want one formula to be absolute, and later we will be wanting those finitely many formulas to be absolute. The other thing that was asked was, what did I mean by if for every m and so on? I mean by that, if we can prove that from ZFC. So if this line is provable from ZFC, then we will call the formula absolute between the two. The other thing that I wanted to mention is that chapter 12 of Yech roughly contains what we are talking about here. It contains more. The same can be said about chapter 4 of the 1980 edition of Koenen's book. And chapter 5 of that book contains a way of defining elementary substructures for set theory without actually quantifying over all the formulas, because that is a big no-no in set theory. We cannot state a theorem like, for every formula this happens. Well, we can state it like that, but then it wouldn't be a ZFC theorem. It would be infinitely many theorems, one for every one of those formulas. But there are ways of getting elementary substructures for set theory, avoiding formulas. And you can read that in chapter 5 of Jech's book, of Kunen's book. And Jech's book, chapter 13, has some of that too. It talks about Gödel operations. And they go a long way toward helping to find those elementary substructures, if you are interested in those. Okay, so here is the absoluteness. I cannot say much more about this other than we will see it in action most of the time. All right. We need to talk about, say, the closure properties of absolute formulas. Easy to check. Here is an instance of what I talked about in the first hour. We want to do things using sort of complexion or length of formulas. And if we prove this, well, this doesn't really need any proof. You fill it in, you stick it in the condition, and it almost proves itself. But then suddenly we have absoluteness for if we don't use any quantifiers in our formulas, we get many absolute formulas in this way. And there is no trouble here. The point being that if phi has no quantifiers, then it looks like M1 element of M2 or something like this. Well, those things relativized were just the things themselves. So you don't really have to hang an M on a quantifier-free formula. It's the formula itself. So that's easy and also not very useful because a little bit of interesting set theory happens with quantifiers. So what about quantifiers? Well, for example, here is a formula, and it expresses that there is an unordered pair. Z is the unordered pair of x and y. Being a subset also is governed by quantifiers for every z. And suddenly, the absoluteness becomes less clear, because if we know that can we guarantee that x is a subset of y in N if and only if x is a subset of y in the real world? Well, no. And here is a very easy formula, easy example. You can cook up many examples like this. If you look at, I mean, this is a ridiculous example. The set is not even transitive or anything, but that's the whole point. If A is a subset of the empty set in M, because every member of M that is a member of A is in the empty set, because there are no members of A in M. And of course, in the real world, A is not a subset of the empty set. So here we have a problem. Being a subset is not necessarily absolute. However, I mentioned in the beginning that we'd be looking at transitive sets. Assume suppose they are transitive, those M and N. And phi is absolute for our pair of sets. Then a bounded quantification. So the official definition of there is an X in Y such that is there is an X in Y and phi. This is absolute for M and N as well. Again, let's see. The formula has a few free variables, and they are among X, Y, Z1 up to Zn. And what is the relativation what do we get when we apply the relativation thing to this there is an X in Y formula? We get this. Or we could even put the M, we could hang it on the little phi. So this is what we get when we relativize our formula to M. Okay. So now suppose we have a few members of M, and by transitivity, if we have, because the M is transitive, if we say there is an X in M such that X belongs to Y, etc. The Y should also belong to M, of course, because we're going to be looking at we're going to substitute stuff from M in the formula. So we assume that the Y and the Z's are going to be replaced by something in M. And why not simply assume that Y is in M? And so the relativation is the relativation that we had now becomes simply there is an X such that this happens. Now we use the assumption that phi is absolute between the two models, between the two sets. Phi m xy m1 up to mn and phi n xy m1 up to mn are equivalent. And so we can simply replace the phi m by the phi n. And by transitivity again, this means that there is an X in N such that this happens. So this now is by transitivity again, we find that if this is true, then we can put the quantifier in N. We can let the quantifier range over N. Okay. So we
Can I
call,
ask
yeah.
something? We really need transitivity of N here because we already know that X is in N because of M being a submodel.
No, this is a row of equivalences. I assume that okay, if I were to write this down in a nice way, let me. These two are equivalent because these two are equivalent.
Yes.
And these two are equivalent by transitivity of N. Because the X, I never chose an X. There might not be an X that does this. The formula might be false, the first one.
Okay.
And then The second one is false by equivalence of the things in the middle.
Yeah.
And then the third one is false by the transitivity of n.
All right.
And if the first one is true, then again, we get the same kind of argument.
Yeah, okay. Thanks.
So yeah, we like I said, it's supposed to represent a sequence of equivalences. Alrighty. This gives rise to a special family of formulas. We call them delta zero formulas. The delta zero notation, I think, is due to Levy from somewhere in the 60s. All quantifiers bounded. So what does it mean to be a delta? These two are delta zero. If I have two delta zero formulas and I take the negation of one, or I take their conjunction, then I get a delta zero formula. And if phi delta zero, then in this case, I choose to put the universal quantifier there as well, because otherwise I would have to formally take all the negations in there anyway, and that might spoil the formula a little bit. Anyway, these are the delta zero formulas, and as always, the delta zero formula is formulas form a class of formulas that contains those atomic ones and are closed under that, and it's the smallest family of formulas with that property. And so the main theorem is this is a huge thing, because very, very many things can be written down in delta zero form. So whenever you have something that can be written down in a delta zero formulation, you know automatically that it is absolute between transitive sets. And so part of the group interaction is write down delta zero formulas for all kinds of things that you have seen thus far. For example, if you look at the axioms of set theory in Yech's first chapter, then all the quantifiers in there are unbounded. Okay, one or two are bounded, but most of the axioms are written with unbounded quantifiers. But practically all of them can be rewritten in delta zero form. That's a good exercise to try. And I put in my notes a long list of things that are delta zero, but in Yech, there is lemma 1210. Many things are delta zero. And one of the reasons I put the 7 axioms in our list of formulas is that sometimes you need 1 or 2 of those axioms, occasionally an instance of separation, to actually show that the original definition has an equivalent delta zero formulation. But that will not be too important for us. So I'm skipping those fine points. Just if you're able to rewrite some of the things in terms of delta zero formulas, that's a good thing. That's a really good exercise. And there are very many things that can be written in that way. I'm not going to write everything down. Okay. You can also write an ordinal in delta zero form. And that, okay, I put it in the group interaction, so you'll have to read that. But it illustrates a point that I made just a few seconds ago. You can write down an equivalent definition of Z is an ordinal if you assume the axiom of foundation, the axiom of regularity. And I'm not going to give anything else away because I want you to think about it yourself, to see what you need to do to get rid of a potential unbounded quantifier in the definition of an ordinal. Like I said, I really want you to think about it yourself. But once you know what an ordinal is, and you could do it delta zero, you can also do limit ordinal, successor ordinal, omega. You can write down an equivalent definition of omega that only uses bounded quantifiers. And you can also write down for every natural number a delta zero formula that actually characterizes that natural number. The problem is that the formula gets longer as the number gets bigger. If you want to express Z is a googolplex in a formula, then that formula will have to be at least googolplex long, and I don't invite you to write that formula down at all. Okay, now we're going to get very close to elementarity, as was mentioned in the break a few moments ago. So the delta zero formulas are a rich source of absolute formulas. Are there things that are not absolute? Yes, and those are the things that we can force to be true or false. X is uncountable is not delta zero, and it's also not always because there are always large enough transitive sets where it does work. So what may happen is that if you relativize the statement X is uncountable, you find that it is true in M. You relativize it, you find a true statement, and then you look at it again, but outside of M, and you find that it's completely false because X happened to be countable. And the question is, how on earth is that possible? Well, there is also something in the group interaction possibly to make you think about that. But we'll get to that. We'll get back to that in the later weeks anyway. Okay, we need a criterion for absoluteness, but we need absoluteness for many formulas at the same time. Okay, so suppose we have a list of formulas and every subformula of every phi I is also in the list. Okay, then we can prove the following, and this is this is quite close to elementarity, but only elementarity for this particular set of formulas, so to speak. Equivalent are for all the phi I are absolute for M and N. B suppose one of our formulas in the list is actually an existential quantification over for another formula in the list. And all the free variables are shown, then, and this also takes a little time to digest. Then the following holds for all tuples in M. This. Okay, and you have to look very closely at what I'm going to write down now. Oops, I got a wrong letter here. there is an x such that phi nj of the x and the mk and the mi's holds, then I have to keep my letters straight. This is what, okay, let's look at this a little bit closer. The first thing you need to notice is that there are two n's here, two Nicholases. You would expect maybe behind the arrow for there to be an M in the formula, but that's not what's going to happen. So this is something that happens completely inside of N. We relativize the formula only to N. We stick in the constants from M, and then we ask ourselves, is there a member of N that makes the formula valid? If so, then there should also already be an element of M that makes the formula valid. This is a little bit like the example with the rationals and the reals. If there is a solution to the equation y squared is equal to 2 in R, then there should be one in Q. Well, no. So in that particular case, this is not the case. But if you take the field of algebraic numbers, then whenever you stick in algebraic numbers in an equation like that, and it has a solution, then it has an algebraic solution. That is what is happening here. If a system of equations with parameters in the small set has a solution in the big set, then it also has a solution in the small set. That is how I think of this all the time. How you may think of it will become clear in the future when you work with it a little bit more. Okay, now let's try and prove this. At least one direction, and then we'll have a break. We'll take the easy direction first. So take our parameters in M. So assume we have this. Okay, take an M. Take such an X. No, sorry. Suppose we have this. That means oops, now my letters are getting confused. Notice that this is just phi I n. So we see that phi I n is true of the points m1 up to mk. Oh, but phi I is absolute. We are assuming that everybody is absolute. So by absoluteness, phi I holds. Or and now I forget my X. I'm getting a bit sloppy. I simply wrote down what phi I M means. But absoluteness, the formula phi j is absolute as well. So phi j m x m1 and so on is the same as the phi n j x up to m1 up to mk. And there we have it. We started out with the assumption that there was a solution in n. We end up with a solution in m. Okay, we'll have a break. And after the break, we do this. And after that, it's relatively easy sailing. This is the most difficult result that we talk about today. We have had models, we have had absoluteness, and the third hour will be devoted to reflection. And I'll pause the recording now. Okay, here we go. As Cheng Lao mentioned, this looks very much like the Tarski-Vaught criterion for elementarity. And this is actually, for those who know this, this result is essentially due to Tarski and Vaught about absoluteness of formulas between structures. It kind of reduces, I already spoke in that type of language a few moments ago. It reduces the absoluteness to, if there is a solution to a certain equation in the larger structure, then there was already a solution in the smaller structure. And that suffices for elementarity. It makes, for elementary substructures, and in our case for absoluteness, it makes checking absoluteness easier. And it also makes, as we shall see in a moment, guaranteeing absoluteness easier. Well, easier, easy. And why did we assume that the set of formulas was subformula closed? Well, we need to show this absoluteness statement for all formulas in the list. That's the whole point. We're not talking about just one formula, no. We're talking about all the formulas in the list. And so we want to show that for all formulas in the list, we have the absoluteness condition. Well, atomic that's clear because the M and N are not important there. Likewise, If my formula is a conjunction or a negation of smaller formulas, then we apply the inductive assumption to the smaller formulas and we're done. So the only thing the only real problem is this. So phi I is this, and by that I mean that, of course, phi I has free variables. They are among y1 up to yl, and it's of the form there is an x phi j. So x is presumably another free variable for phi j. Okay. Okay, I'll identify the variables with the members of M. So take members of M. Let's not overload our letter quantity too much. Oh, wait. We look at phi I, y1 up to yl. The definition tells us that this formula is equivalent to this. The inductive assumption tells us that we can replace the phi m by the phi n. Why is that? Well, if there is no, I mean, we have an equivalence here. It could be that the phi I is false, and that means that there is no m. Well, if there is no m such as this happened, then there is also no m such as that happens, because we don't have an x to worry about. If it is true, there is an x, we pick it, phi mj x y l and so on holds. That means that phi nj x and so on holds, and we have an equivalence by the inductive assumption, because we assumed that we already had absoluteness, that phi j was already absolute. Our assumption B now tells us we can replace x in m by x in n, and well, we don't change the formula. This is what assumption B tells us. And there we have it. We start out with phi I relativized to m, stick in y1 up to yl, see what it means, translate it using the inductive assumption, translate it once more using assumption B, and then say, but wait a minute, that was phi n, phi relativized to n with y1 up to yl included, and there we have it. So the proof is actually not very difficult, as long as you do it by induction on the complexity. And some of you who have seen this in your logic classes, this works for all first order in any first order situation. So it also works for fields, groups, vector spaces, whatever. And we use it for set theory. And like I said, it's time for some reflection. Because what? Well, we have our formulas, and I promised you that we could find a V alpha. We could find many, well, V betas for such that the formulas were absolute. And now it's easy to do this. We look at our formulas, and we assume that they are subformula closed, and that we also have those other axioms, but they're not really necessary. So we assume our list is subformula closed, so we can use the Tarski-Vought criterion if we want to find V alpha such that the formulas are absolute for that V alpha. Then okay, I'm not going to write that down in formal language. That's why I put it in quotes. Give me an ordinal, I'll give you a bigger one, such that the formulas are absolute for the corresponding V beta. Absolute, that's our list of formulas, but our list of formulas were axioms. So for our axioms, okay, so we can take a list of formulas and prove this. Then we can say, but wait a minute, our formulas were axioms. If we have a bunch of axioms for ZFC, then we can find for every ordinal alpha a larger ordinal beta such that the axioms are actually true in the corresponding V beta. And this comes quite close to what I said we were going to do at the beginning. We were looking for a set such that all our formulas were true in that particular set. The only thing that we don't have yet is that the set is countable because the V betas are quite big, but let's not look a gift horse in the mouth so far. Let's see what we can do with, let's see if we can do this. Okay, so we apply the Tarski-Vought thing with n equal to the universe V. And so our formulas relativized to the universe are just the formulas themselves. And if our formula is of the form existential quantification, then we can define our formula is an existential quantification. So it might be true, it might not be true for the yi up to yl. If there is no x, we set g of I of our things to be equal to 0. If there is an x, then we take the rank of, we take the first eta such that there is an x in V eta with this property. We don't choose the x, we only choose the rank of some potential x, and we don't need the action of choice here, so to speak. And we can take the supremum of all those ranks, and that'll give us a new ordinal. And then we're done. Basically, alpha given, beta 0 is alpha. And what kind of letters do we still have left? Given beta k, put beta k plus 1 . Oh, k was forbidden. Too bad. We have our beta p, and we look at the functions f1 up to fk, because we have, yes, we had k many formulas. Each one of those formulas gives us an ordinal, and together with the beta p, and take the supremum of all those beta p's. How does that help us? Well, apply Tarski Vought to V beta and V. Because what did we need to show? Where is our condition B? For every formula, if it is of the form there is something, then for every element, for all the elements of M, if there is an X in the big structure with a certain property, then there is an X in the small structure with a certain property. But notice we had the same N here, and this is where this becomes important. Why do we apply Tarski Vought? Because we know we simply make this true. If we have some points in V beta, then they are in a V beta P, and then there is an X in the V of beta P plus 1. Let me. If the points y1 up to yl are in V beta P, then the X we can find in V beta P plus 1. So we have done what we promised. The Tarski-Vought criterion tells us we have accomplished our goal, at least if we don't worry about countability. We have a transitive set such that all the axioms hold in that particular transitive set. It happens to be a V beta. And the only thing we still have to do, and we have 15 minutes to do that, and it's going to work like a charm. Now we want a countable M. And here is where we apply the axiom of choice. And we're going to apply it really, really strongly. We still have our list of formulas. If, okay, I was a little bit sloppy. I defined the functions only if the formula started with an existential quantifier. If it doesn't start with an existential quantifier, we simply take the function constant 0 because we don't have to do anything anyway. And the same thing is going to happen here. The if is a little bit premature. We take a well order of V beta. Okay? This works for any V beta that has our formulas absolute for it. So, right? We define HI from if phi I it happens to be okay, the L depends on the I. Let me try and be precise just once. We define a function from V beta to the power Li to V beta and we do the same thing as before. If there is no X for our Y1 up to YL, don't do anything, just send Y1 up to YL to 0. If there is an X, we take the first one. This is where we use choice. We well order the whole thing, and if we have witnesses, we take the first witness in our for our formula. Okay, right. Now what? Well, We could even take a small subset of V beta, meaning that the cardinality of X is not too big. Actually, it doesn't really matter what the cardinality of X is if you look at the proof, because what we know is that V beta is closed under all the mappings F. Here's what we do. We still had our K formulas. So if our formula is not existential, we just choose 0. So then nothing interesting happens. And I do need to put the Li between in the brackets. Like so. We take X, we take all the function values for all the Li tuples, for all the I in X, add them to what we have. And we keep adding, we keep adding, we keep adding. And in the end, we union up all the ANs. What do we know? Well, A is closed under the workings of HI for every I. Now, if you look closely, you'll see that we had finitely many functions, not too many. We did countably many steps, and we started with a function with a set of cardinality. Well, could be finite, X, could be infinite. But what we get is that the cardinality of A is at most the cardinality of X or LF0. If X is finite, then all the ANs are finite and A is at most countable. If X is infinite, then every one of the ANs has the same cardinality of X. And so the cardinality is LF0 times the cardinality of X. And all formulas all our formulas are absolute for the pair A, V beta. So A is countable. Is A transitive? Probably not. But now we do the last thing. And I looked back in the lectures, but I didn't see it. And if you want to see the full theorem, you need to go to theorem 615 in Jech's book. We have the axiom of foundation all the time. So the element of relation is well founded on A, and we can define a function from A to V by a recursion like so. If we take, so if y is minimal in A, then pi of y is empty because there is nothing below it in A. And then we divide A into layers and we keep on defining the value of the function according to these layers. And if you look at theorem 615, you'll see that it's just like defining a function by recursion, but now we use the well-founded element of relation. And in fact, because we have all those we can add a few axioms. We can have this. We can simply have V omega be a subset of A. And if we do that, then at least the bottom part of A is quite nice. It is V omega. But anyway, we can define this mapping, and by replacement, M is a set. And remember, extensionality was in our list. And it's an element of isomorphism. X is a member of Y if and only if pi of X is a member of pi of Y. And that gives us finally what we were looking for. For all the axioms in our list, phi I of M is equivalent to phi I of A is equivalent to phi I of V beta is equivalent to phi I. But the phi i's were axioms, and so they're true. And that means the phi i's are all valid in M. And that is what the goal was for today. You give me finitely many axioms of ZFC, and I'll show you how to build a countable structure where we interpret element of by element of. So we simply get a countable set. And inside that countable set, all those finitely many axioms are true. Now, in the group interaction, there is a question at the end. I don't want to give too much away, but that group interaction question, I think I'll write it there. Skolem's paradox. You may have heard of it, and you can Google it now if you want to. If we put enough axioms in our list, then in M, in M, we can create the real line. We can actually make it so that the real line becomes a member of M if we take some canonical construction of the real line using dedekind cuts and quotient fields and whatnot, starting from the natural numbers. Then we get an uncountable member of M in a countable universe. Think about that for a week, and maybe next week we'll talk about it a little bit more. It has something to do with the non-absoluteness that I mentioned a few moments ago. Uncountability is non-absolute, and that has something to do with the resolution of Skolem's paradox. Okay. I think I have nothing more to say. I could summarize what I did today very quickly, but that would just, well, maybe just to recapitulate. We started with a finite list of axioms. We needed to talk about validity in sets. We did that. And so the first thing we did we found many V betas such that the phi's hold in V beta, or so we could do the relativation business. Then we found A. Then we found a countable subset for which those formulas were absolute. So that meant if the formulas hold in V beta, they also hold in A. And then M, okay, if you go to Jech's book to 615, this thing is called the Mostovsky collapse of A. That's isomorphic to A. And so the phi 1, okay, hold in A, hold in M. This whole construction could be done in a formal proof in ZFC. And so what are we going to do next week? Take such an M and extend it to an N in which our phi's still hold. Okay, I'm cheating a little bit, but I'll get to that next week. And also the formula that expresses not CH. And once we have done that, I'm not going to say that we're going to do this all next week. Next week, I will show you how you can extend such an M in general. And maybe along the way, I will try to keep the example illustrated by means of the example that we'll use to force not CH. And then in the other weeks, we'll look at the example of not CH more closely. We'll try to see if we can make CH true also in some model. And maybe, if we're lucky, we can do one or two more examples. But for now, I'll put up the homework and the group interaction files tonight after some of the corrections that I got from the colleagues. And Well, see you next week.
Excuse me, KP. Excuse me.
Yeah, one